So here we're going to take a look at Pauling's rule number 5, the rule of parsimony. And this is an interesting word choice. Parsimonious means to be stingy. So it's in a sense Pauling's rule of stinginess. And we'll see that what he means by this is that crystals are stingy about how they arrange themselves into various units of polyhedral elements. So we have a couple of polyhedral elements here. We're going to use this very nice diagram of the amphiboles from Klein and Dutroux. And to illustrate what's going on here and this rule, we'll take a look at the generalized formulas. The generalized formula is usually written something like this, where we have a W that has 0 to 1 atoms, and then 2 X atoms, 5 fellows that we refer to as Y, and then a Z, and we'll take 8 of those, 22 oxygens, and then we'll complete the charge balance by taking 2 of either a hydroxyl or a fluorine. So that's the generalized formula. And of the 92 naturally occurring elements, a very large fraction of them can fit somewhere into this formula. But think about this. If we can put, let's say, 80 of the 92 elements easily into one of these various sites, how is it that we get this rather simple formula? Now, this is certainly more complex than something like SiO2 or CaCO3, but there are a lot of different ways that we can arrange 60, 70, 80 different elements, and yet we write this very, very simple formula. Well, to see what this means in a Pauling's rule sense, we can think about how these fellows relate to specific sites. So we have a couple of sites here. We have, in general, an octahedral site. So that would be this guy here. It has 8 sides. You can't see all 8 of them. That 8-sided coordination, it's a 6-fold coordination. Those 8 sides come from the central atom being bonded to 6 different atoms. Then we have these tetrahedral sites. We'll call them a T. The tetrahedral sites come in 2 different flavors. So we call them a T2 and a T1. And then these octahedral sites, we could use O, but since we fill them with metal cations, we'll use M. And we have 4 different sizes. There is the largest M4, and then a little bit smaller M1, and then we have the M3, and the smallest is M2. And then we have these large open A sites. These A sites are the center of these rings that are formed by the tetrahedra. So you can see these tetrahedra are corner sharing, and as they share corners to make these 2 chains, remember amphibole is an enosilicate, we have 2 chains of tetrahedra, we have this ring structure, and the A site is there. Well, the W elements go into the A site. These fellows that are in the X position here in the formula occupy the larger M4 site. So that's an M4 site here, just like this fellow here. The atoms that would be situated over here in the Y part of the formula, those 5 atoms would fill up all of the other M sites. So the M1, M2, M3, those would be the Y atoms. And then the Z atoms would occupy the T1 and T2 sites. And then the oxygens form the corners in all of these. So we'd have an oxygen there, and there, and there, etc. Except where we have these dashed circles. Those dashed circles could be an OH, so we could have another oxygen there with a hydrogen attached to it, or it could be a fluorine atom playing the charge balance role of hydroxyl. So what are the elements that go here? The W site being very large, you could take large atoms like sodium or potassium. For things like the Z site, the T sites or the Z elements, those are going to be the highly charged and smaller silicon and aluminum atoms. And then the X and the Y are going to be various kinds of transition metals. Titanium, manganese, some nonmetals also. Aluminum can go into the Y site. Fe3 plus would go here. Fe2 plus would go in the X. Fe3 plus. We'll talk about amphibole chemistry a little bit later. The bottom line is all of that very messy chemistry can be referred to by this simple formula. So we're going to take 60, 70, 80 possible elements, and we can think of them as a small number of constituents, as an M1 constituent or an M2 constituent, something, or in other words, from a chemistry side, we could talk about a W constituent. We can use this word constituent in a couple of different ways. Originally, I think Linus Pauling was talking about the kinds of polyhedra that anions would be connected to. But I think it's possible to usefully broaden the idea where we talk about either chemically a W, X, Y, or Z constituent, or from a structural standpoint, an M1A or T2 kinds of constituent. And these constituents are very small. So even though we have lots of different elements that can go into a very messy amphibole formula, we can talk about just a small number of constituents. How many are there? Let's end by just counting them out. We have 1, 2, 3, 4 different places where we would put any number of cations. And then in terms of numbers of sites, we have 4 different M sites. So we have 4 M's, and then we have an A site, and then we have 2 different kinds of tetrahedral sites. So altogether, we have 7 different types of sites. So we could talk about having 4 kinds of chemical constituents or 7 kinds of structural constituents for an amphibole formula that is otherwise very messy and can partition a very large number of the naturally occurring elements in the periodic chart. So that's what he means by parsimony. There might be a lot of things we can put into a formula, but we're putting them into a crystalline structure in a small number of structural ways.